A distant whine rises over the landscape, a small, precise sound that belongs to a new kind of machine. It is the sound of a military drone taking flight, an aircraft without a pilot on board, but with a purpose very much decided by human hands. In this video, we will trace the invisible threads that make such a machine possible, the engineering of the A-frame and propulsion, the sensor suites that let a drone see, the communications that let operators steer from afar, the software that gives it autonomy, and the ethical and strategic questions that trail in its wake. Understanding how military drones work means looking at hardware, software, and doctrine together, and seeing how each informs the other in modern warfare. Before we start the video, make sure to like and subscribe to our channel for future updates. Let's start the video. At the heart of every drone is its A-frame, the physical body that carries everything else. A-frames come in many shapes: tiny quadcopters that can hover between buildings, fixed-wing platforms that cruise for hours at high altitude, and hybrid designs that combine vertical takeoff with efficient forward flight. Materials matter. Composites and light alloys keep weight low while preserving strength, and the specific form of the A-frame is chosen to match the mission profile. A surveillance drone emphasizes range and endurance. With wings and an efficient engine, a tactical drone intended for urban operations prioritizes maneuverability and small size. Even the shape of a drone can be a tactical decision, affecting its radar signature, speed, and payload capacity. Propulsion systems give drones a motion and endurance, and they range from electric motors powering rotors to turbine engines for long-endurance systems. Electric propulsion is quiet and responsive, making it ideal for small reconnaissance platforms, while internal combustion or turbofan engines are used on larger drones that need to cover thousands of kilometers and carry heavier payloads. Fuel efficiency, noise, heat signatures, and maintenance all influence the choice. For endurance missions, engineers balance fuel capacity with weight and aerodynamic efficiency. For short-range tactical strikes, acceleration and responsiveness can be more important than flight time. What transforms a flying platform into an intelligence, surveillance, and reconnaissance system is the sensor suite. Cameras remain central, electro-optical sensors for daylight imaging and infrared sensors for night operations. But modern military drones also carry synthetic aperture radar to image through clouds and smoke, signals intelligence packages to intercept communications and emissions, laser rangefinders for precision targeting, and environmental sensors to detect chemical or radiological hazards. These sensors feed enormous streams of data back to operators, who must sift, interpret, and act on what the drone reveals. Advances in miniaturization and computing have made it possible to stack multiple sensor types on a single platform, making drones versatile tools for battlefield awareness. The nervous system of a military drone is a communications and data link architecture. Secure radio links, satellite relays, and line-of-sight transmissions connect the aircraft to ground control stations, allowing human operators to pilot the drone, adjust sensors, and receive imagery in near real time. Encryption and anti-jamming measures are essential. In contested environments, communications must survive deliberate interference. Some drones operate within a local network, passing data through relay nodes or other drones acting as communication hubs, while strategic systems use satellites for beyond line-of-sight control. The vulnerability and resilience of these links often determine whether a drone can complete its mission or be rendered ineffective. Control and command can be centralized or distributed. At one end of the spectrum, a pilot in a ground station or in a remote operation center sends commands, views live feeds, and makes real-time decisions. At the other end, autonomy takes on increasing responsibility. Autopilot systems manage flight control, obey no-fly zones, and execute pre-planned routes with precision. Machine learning and onboard processors can reduce the cognitive burden on operators by performing tasks like target detection or threat classification. Yet autonomy does not mean humans disappear from the loop. Rules of engagement, mission parameters, and legal restraints still require oversight, and designers build systems to allow for human intervention when needed. Weapons integration is a defining capability of many military drones, and it requires a careful marriage of guidance, payload, and targeting. Small armed drones can carry loitering munitions or lightweight guided bombs, while larger platforms mount precision-guided missiles and smart bombs. The launch mechanisms, targeting sensors, and fire control software must operate in concert, often under constraint that the platform itself is exposed to countermeasures. Precision depends on a combination of onboard sensors, external targeting data, and GPS guidance, An increasing emphasis is placed on reducing collateral damage through better discrimination and abort mechanisms. The result is a weapon system that can strike from great distance with a level of persistence human-crewed aircraft rarely match. A major shift in recent years is the rise of autonomy and the concept of swarms. Autonomy allows drones to fly complex patterns, avoid obstacles, and even retarget themselves if conditions change. Swarm tactics deploy many small drones working together, communicating locally, sharing sensor data, and coordinating behavior to overwhelm defenses or cover wide areas. Swarms introduce new challenges in communications, collision avoidance, and command distribution, and they raise difficult questions about accountability and control. Engineers are developing algorithms that let swarms adapt to lost members, reconfigure missions on the fly, and balance redundancy against the need for centralized oversight. Counter-drone technologies form the other side of this technological coin. Radar systems and optical trackers try to detect and classify drones as they approach, while electronic warfare systems attempt to jam or spoof their communications and navigation signals. Kinetic measures, from nets to interceptor missiles, also exist for neutralizing hostile drones. The contest between drone designers and countermeasures creates a constant cycle of innovation. Smaller signatures, decentralized control, and hardened communications are met with better sensors, network defenses, and smarter electronic attack tools. The battlefield becomes a layered environment where detection, deception, and resilience decide capability. Beyond the mechanics and tactics, military drones force us to confront moral and legal questions. The ability to strike or surveil at a distance reduces risk to one's own forces but raises the threshold for committing force, complicates attribution, and can erode traditional boundaries between combatants and civilians. International law struggles to keep pace with machines that operate semi-autonomously and across borders. Policymakers, military ethicists, and technologists debate where to draw lines on autonomy and lethal decision-making, and whether existing rules of engagement are adequate for a world in which decisions are made faster and at greater remove. Finally, the story of military drones is also a story of shifting strategy. They change how militaries gather intelligence, target adversaries, and project power. They enable persistent observation over remote theaters, rapid response to fleeting opportunities, and decentralized tactics that leverage autonomy and networked operations. As the technology matures, smaller nations gain capabilities that were once the preserve of major powers, reshaping the global balance. Whatever the future holds, the essential truth remains. Military drones are not just machines in the sky. They are systems, physical, digital, legal and ethical, woven into the fabric of modern conflict, demanding careful stewardship as they reshape the character of warfare. The wine fades as a drone climbs beyond sight, but its implications do not. In the quiet moments after takeoff, engineers and commanders, legislators and citizens alike must consider how these systems will be used, who will control them, and what limits a society will place on the machines it creates. Understanding how military drones work is the first step towards shaping that debate, because only when we know the mechanics of possibility can we responsibly decide the rules of engagement for the technologies that are rapidly redefining the battlefield. I hope you enjoyed this video. If you did, make sure to like and subscribe to our channel for future updates. See you in the next video.